So our next talk will be defining a data masking framework at scale. In this talk, we'll explore tokenization and obfuscation as alternate data security techniques in addition to conventional methodologies like encryption and the challenges that need to be addressed like implementing a data security framework at scale. We have Sohini on the left. Sohini is a senior security partner at LinkedIn. Sohini is a Purple Team evangelist and is also passionate about data security and cloud security. She has been a speaker at BSidesSF San Francisco 2020 and has also spoken in several other conferences. I'll now pass it out to Tim.
Thank you. I'm Tim. I'm a data security architect, and I haven't done this before, so hooray.
Hey everyone, I hope you are doing well and enjoying the BSides conference. Today we'll be talking about defining a data masking framework at scale. I am Sohini, and with me I have my co-presenter Tim.
So today we're going to walk you through an example of data security over time, how it evolves, how the needs and the usage of the data change. And we'll be going through data privacy and how that interacts with data security. And we'll go over some strategies that we didn't touch upon during our example evolution, and then go through some gotchas that kind of apply to all the strategies we've outlined.
Okay, so the year is 2015. Our example company, Real Corp, is collecting various information about the global workforce. Now, this sensitive data is being used in a variety of jobs and workflows to power the platform.
The data is stored internally, and it's made accessible to all engineers because it's faster to develop that way. And as far as the company knows, there are no legal regulations that restrict handling of the data.
Fast forward a few years and GDPR comes along. It requires that companies implement strict technical controls to protect personal data. Now, using this as an opportunity to reevaluate data protections, Real Corp's legal team ascertains that salary is indeed super sensitive and that it might need more protection. After careful consideration, they decide to encrypt the entire data set. Now, this is easier than doing targeted or field-level encryption and offers similar level of protections.
A feature team wants to start running analytics on this data. They want to see feature engagement in regions A versus B, but they don't care who the users are or what their salaries are.
So our previously selected protection of encryption falls a bit short here. While the data is protected against unauthorized access, we do have a very valid use case, that is the one running analytics that doesn't need access to the raw data and has the ability to leak keys for the entire data set. So to help shore up protection, Real Corp makes a copy of the data and hash certain fields like user ID and name. This maintains uniqueness without providing the ability to read the raw data.
Eventually, though, someone discovers that we've got two copies of the same data and says, man, we could definitely do better. We need to tear that down to one. So we reevaluate our protection mechanisms. Encryption has been useful in stopping unauthorized access, but it doesn't allow you to run analytics without access to the raw data. And hashing allows you to run analytics, but transforms the data, making those analytics fairly limited.
Now, also hashing is vulnerable to many known attacks, right? So by adding a record with known input, such as creating a fake profile with the name Sohini and finding that entry somewhere in the resulting output, it's possible to de-anonymize the data.
Additionally, if the hashing algorithm is known and the input space is small enough, you could potentially create or use an existing rainbow table and de-anonymize the data. Additionally, when you hash data at scale, it typically introduces a really large time delay, which is rarely acceptable.
Okay, so we understand that the combination of hashing and encrypting isn't ideal. So Real Corp settles for a special type of encryption called format preserving encryption. Now, FP encrypts the data, that is, it prevents unauthorized access to it, and retains the format of the data in terms of its length and character positions. Now, what it does is that it enables analytics to be run on it without the need to decrypt the data. By using this method, we can potentially eliminate the redundant second copy of data that we were referring a couple of slides back. And it also comes with an added benefit that we can implement it fairly seamlessly on legacy systems like databases or applications without the need for changing field sizes or formats.
So we've got a lovely picture here of some of the more well-known sensitive fields like social security numbers or credit card numbers, but format preserving encryption can be done on other things like IP addresses as well. Okay, so fast forward a couple of years again, and we've discovered that this encrypted data has been actually written in clear text. The incident response team does an investigation and finds that authorized users have written that data by mistake in clear text because the encryption wasn't done automatically for them. So let's go looking for another solution. We settle on tokenization. In this usage, tokenization involves sending data to a server which generates a random placeholder value, optionally sharing the format, and returns that value back to the caller. This data can be used to perform specific operations, but because it's random data linked back to the original data, there's no way for anyone to be able to operate on that data outside of the context that we deem acceptable. We can also centrally monitor all usage of that data since it requires accessing the mapping table.
Okay, so now RealCorp's management has struck up a deal with a third-party ad provider. In order for them to serve ads accurately, we need to permit analysis on our sensitive global workforce data. But we shouldn't be sharing our raw data with the third party just like that, right? So let's walk through some of the attributes that we want our system to have when we are sharing sensitive data with an untrusted partner. Now, this isn't really limited to third-party data sharing and can be extrapolated to minimize unintended exposure of sensitive data each time it crosses trust boundary, say, for example, to a lower security domain, even within the same organization.
We want a solution which is one way, such that the shared data doesn't get leaked, even if the keys used to protect that data were leaked, compromised, or otherwise shared. Additionally, since our example here is for ads, we need to ensure referential integrity, which means when the same input is provided, we need to provide the same output. And lastly, we need ongoing key rotation in order to ensure ongoing protection of that data.
So key rotation poses its own challenges, right? Only being done for the most sensitive of data or when a breach is glaringly obvious. And this is due to the associated cost and complexity, which really scales with the volume of data that's being protected. Now, if you combine this with referential integrity, that is the need for the same input to map to the same output, and you have a very large sphere of compromise if any key is ever leaked. Now, a key update must maintain consistency with respect to the data being masked by the new key and the data that has been already masked by the previous key, right? Now, really a key update might be easily done by simply rekeying the entire data set at once. But that really doesn't work in a real-life scenario, as that will pose data usability or availability issues.
So let's see if we can push the need to rekey onto the destination rather than doing it ourselves. We're going to look at a paper authored by some people over at IBM where they describe a set of algorithms that use encryption and hashing in order to dynamically update the protection of data.
So let's look a little more into the details now. As Tim mentioned, the setup considers a data owner producing data and tokenizing it, the one that we refer here as a source, and an untrusted host, that is destination, storing the devalued data only. So the scheme operates in epochs starting with E0. As a first step, the owner generates a new tokenization key for E0, referred here as key 0, and it uses it to tokenize any new values that's added to the dataset. The owner then sends the devalued data to the untrusted host. And now it repeats it for the next epoch, that is E1, and so on. The owner at this stage also sends an update tweak to the host, thereby rolling forward the values tokenized for the previous epoch to the current epoch. Now, it's really a very complex set of algorithms that we have tried to represent on a high level in this slide because of time constraints. But if you're looking to solve similar problem statements in your organization, we highly recommend you to refer the paper, the link to which has been linked at the bottom of the slide, and explore it further. Now, before we move on, a point to be noted in this context is that the correctness condition of the algorithms is such that any newly devalued data from the owner in a particular epoch must be same as the tokenized value produced by the host using the update tweak, thereby ensuring referential integrity.
Okay, let's switch it up a bit now and talk about privacy. For the context of the next few slides, we're going to refer to security as stopping unauthorized actions and privacy as stopping unauthorized use cases.
So user-facing privacy controls are often implemented on back-end jobs. Let's take an example of salary forecasting as depicted by this awesome-looking bar diagram. Now, due to privacy requirements, the salary modeling system has access only to cohort-level data containing anonymized compensation submissions. For example, salaries for security engineers in the San Francisco Bay Area. Let me try to elaborate a little more. Now, I might be very interested in having salary forecasting as a critical data point while zeroing in on my next job. Now, the gentleman sitting over here and the person over there, they might have been generous enough to provide their compensation details to this salary modeling system and for us to be able to gain that insight. But of course, they wouldn't be comfortable being attributed directly or categorized specifically with their data as per attributable to that particular individual, right? So yeah, let's try to elaborate more on what we can do about that.
So in this case, IDs attributable to the user are hashed. Hashing in this instance can be used as both a security and a privacy control. And indeed, often security and privacy controls have overlapping needs and requirements, which means that when you select a control for one, the other needs to be in your mind, or you may end up in a case where you select a security control and the organization is unable or unwilling to implement the matching privacy control.
So next we'll cover one more example of privacy control on user-facing applications. So user-facing privacy controls are relevant to protect certain categories of private actions a user can take, such as clicking on an ad or reading an article. Now, this is very different from a social action like posting an article or sharing a certain article. Let's try to elaborate a little more. Let's say I have a startup which has a next-gen AI security solution. I post an article about this somewhere, say on Hacker News, and I want to see if it's resonating well with leaders in this space. So I go on looking if how many CISOs have read this article in the last couple of months. Now let's say my good friend John Doe at CISO at Real Corp reads this article. Now, John reading this article should definitely contribute towards the stats, right? But again, because of privacy concerns, I shouldn't be able to explicitly figure out that it is indeed John who has read this article. So how do we ensure this?
To ensure this, the platform prevents me from creating a filter for CISOs who have read your article if the results of that filter are too few. I could still, however, set up a filter for people who work at RealCorp and people who live in San Francisco, California, and people who have previously worked at another real corporation and combine those. Despite the platform's efforts, I can still attribute this action to an individual. So the way to protect against that is generally called differential privacy, and it works by adding a random amount of noise to the results of these queries. Now, you can also attack that by issuing the same query repeatedly and averaging out the results to remove the noise. To protect against this, you can use a pseudo-random noise generator where you add a predetermined amount of noise to the query, which gets redone each time the query is run.
So we talked about some common data protection techniques like encryption, FP, tokenization, hashing, and so on. So let's quickly glance through some of the other options we might have. Now, homomorphic encryption allows computations to be performed on encrypted data without first having to decrypt it. Sounds promising, right? So this picture shows one such additive operation for homomorphic encryption. However, this technique has some significant limitations in terms of the operations that can be performed and also has latency concerns and high storage requirements. So because of obvious reasons, it's not mainstream, but that being said, it's still an emerging solution, especially in high security cloud use cases.
AI has been exploding recently in popularity in places such as ChatGPT and Tesla and Uber. And typically models like those are trained while they're being developed on real data. In some cases, it may be possible to build those models on synthetic or completely fake data, and then when the developers have some level of confidence in their models, move it over to real data. Masking is another commonly used technique to protect data. It involves replacing characters of the data with random value with a placeholder value. It's very easy to do and can be done on the fly rather than needing to be done at the data at rest, making it a very lightweight option.
Okay, so Mr. Cat here agrees that data protection and data security is indeed a big deal, right? So we talked about quite a few options, each with its own security properties. So how do we rationally categorize which data security strategy aligns better with certain specific use cases? So since there are so many options out there with different security properties and each with their own caveats and nuances, we tried creating a flowchart to help decide. We focused on a combination of data properties and security needs. Note that the green arrow represents a yes to the question and red is obviously a no. The blue boxes denote runtime protections as opposed to protections applied to the data as it's written to the store. Now, two key points about this flowchart. First, it does not take into account business needs beyond the need to reverse the data. And second, it doesn't handle layering options. For example, if you have unstructured data that needs to be reversed as well, we could enable encryption to protect the data at rest and mask all data from any reads to the data set to protect it in use.
So let's take an example of data which is structured that we need to be able to reverse and we want to protect both in use and at rest. We can see that we say yes to is it structured and yes to it is reversible. That immediately eliminates the options of hashing, synthetic, and tokenized data. We've said that the data needs to be protected at rest, so we can eliminate masking and adding noise. Lastly, because it needs to be protected in use, we can't use traditional encryption or format-preserving encryption. Our vision with this chart is to codify it into something that engineering can use to get some idea of what protections they can use without the delays that are typically involved in talking to security about pretty much anything.
Okay, so through this presentation, we have alluded to gotchas in several of the techniques. We'll now try cover some of these. Let's talk about hashing. Now, hashing is only really helpful if the data domain size is significantly large enough. For example, hashing cities isn't a good idea because an attacker can very easily and effectively use rainbow tables to bypass the protection. Format-preserving encryption may leak data types like IP addresses and may even allow attackers to infer the values based on the surrounding data.
Tokenization has few weaknesses other than the limitations around when it can be used, but if you can successfully attack the token mapping table, it fails catastrophically. Masking is tough to do if you're not doing it to the entire field. For example, it's common to mask email addresses by masking the user alias. If my email address was tim@timsdomain.com and we masked the user alias, we'd be left with *** at timsdomain.com. And that assumes we do the entire user alias, which isn't always the case either. Lastly, our threat models so far have really described problems one at a time with a single database in mind, but it's conceivable that an attacker could gain access to multiple data sets and join those data sets on unique data that isn't protected. So the bigger picture is important to keep in mind as well. Data security is tough. There are legal requirements to do it. There are lots of options to do it, and each of those options has a lot of nuances and limitations. But hopefully we've given you some ideas around what you can do and when. Thanks. Any questions? So the question was homomorphic encryption. Can you explain it a little more? The questioner has heard about it, but not seen it in use.
Yeah, so there's some limited operations that can be performed on it. So there's like additive operation, the one that we had in the screenshot, and there's multiplicative operation as well. And by virtue of certain algorithms, there's no need to decrypt the data, and you can directly perform it on the resulting output.
The only one I don't understand is homomorphic encryption. What does it actually mean?
What does it actually mean is the question.
I understand like how all the other ones work. Maybe I'm just not getting into the links.
Yeah, so it enables you to do computations on the data without knowing what that data is. The slide that was up for it kind of went into the math behind it. I'm not a mathematician. I can't explain to you how the math works. Sorry.
Okay.
Cool.
One other question. You mentioned some of the pitfalls with the different methods, and some of them are format preserving, and that was listed as a pitfall, for example, for IP addresses. There's algorithms like CryptoPan where you can still perform top K prefix searches on the anonymized or pseudonymized data points, but isn't that precisely the trade-off? Because you want to be somewhere in the middle of the spectrum of full privacy and nothing at all. So I think I would have questions, even after the flow chart, is when I'm not at the two ends of the spectrum, but rather somewhere in the middle, like what do I get when I get any of these things? Like, because I do want some extra utility from, say, the structure preservedness, but what do I give away? And like, to me, that navigating that space is would be like the next thing I'd have to do after having heard your talk.
Yeah, I think the flowchart really should be two flowcharts, one where we walk through the data use needs and one where we walk through the desired security attributes being applied to that. But we didn't have time to break the flowchart into two for this talk. To talk about isn't that a plus of format preserving encryption? Yes, it is, but only if you are knowingly taking that on.
Sure.
And that you say, I'm okay with people being able to deduce information about this. For that particular data. Any other questions? I'm sorry, I couldn't hear you. Which of the masking techniques do we what the most?
Which of the masking techniques do developers like the most?
Which of the masking techniques do the developers like the most? Probably what we have described as masking because it is the easiest.
Or none.
Any other questions?
On the topic of developers, how do you handle with format preserving schema changes and the need to potentially roll back if that changes? You push something to UAT, it doesn't work as you expect. How do you deal like rolling it back a change? Say if you need to include IPv6, not just IPv4.
Yeah, that goes more into how we make certain libraries available to the developers to handle that. And I don't have a good answer for you right now.
Let's actually end the Q&A right now. If you have any other questions, you can go ask him outside. Let's give a round of applause for him.
Thank you.